So again, we've been jumping around a little bit, but we're now into chapter 12. I guess let me do this real quick here. So I'm gonna, in the content library here, I'm gonna move all the stuff from supplement A down to the bottom, just so to keep the most recent thing up at the top. Like I've been doing, you might have noticed I did that earlier. Apparently, doing so is going to be like extraordinarily slow right now. I don't know why. Look at my little toolbar, just, oh, there it goes. Okay. All right. So here in chapter 12, we're going to be talking about modeling functions, and specifically polynomial type functions. So let's start with just a little definition. Let's recall what a polynomial function is. So a polynomial function is of the form a sub n times x to the n, a sub n minus 1 times x to the n minus 1, all the way down to a sub 1 x to the first plus a sub 0. Now these a's have to be real numbers, and specifically that first coefficient, we call the a's the coefficients, has to be non-zero. And these n's have to be integer valued and bigger than 0. I guess I should say 0 is okay. So a little aside, a couple of pieces of vocab here. We say that the coefficient a sub n is the leading coefficient. I'm just going to abbreviate that as LC. And we call n the degree of the polynomial. And then each of these pieces that are in between the addition signs, we would consider a term in the polynomial. So let's take a look at a couple of examples, and we'll decide whether something's a polynomial or not. And if it is, then we'll write down the degree and the leading coefficient. So I'm going to write down a couple of examples here, and then we'll take a minute and kind of think about each one and make a decision as to if they're polynomials or not. So here's a couple of examples. Let's take a look at each one of these examples and compare it to the definition we just described above and determine whether these things are polynomials or not. And if they are, we'll state the leading coefficient and the degree. Cool? So let's look at the example A to start. Here it says f of x is equal to 4x to the 6th minus 5x squared plus 2x minus 1. Is this thing a polynomial? Yes. Yeah. So the two things we have to look at the coefficients. If I look at the coefficients 4, -5, 2, and -1, those are all real numbers, so that's good. And the other thing I need to look at is the exponents on my variables. The exponents on all my variables are integer valued and non-negative, right? The coefficients are, or the exponents are 6, 2, 1, and then really there's a 0 there, you could think. Like an x to the 0 there, because what's x to the 0 the same as? That's an algebra 2 question. Nope, 1. 1. Remember, anything other than 0 to the 0 power was 1. So really, we can tack an x to the 0 on it, and it doesn't really change anything there, right? Does everybody feel good? The only other operations going on are like the multiplication in between a variable and a constant. That's fine. Or addition and subtraction. So this thing is definitely a polynomial. So what's the leading coefficient then in this case? 4. And the degree then would be 6. So again, the leading coefficient is the coefficient on the biggest exponent variable. In this case, x to the 6th is my biggest exponent. So the degree is 6, the biggest exponent, and the leading coefficient is the coefficient on the term with the biggest exponent. Okay. So far, so good. Let's look at B. So g of x is equal to the square root of 3 times x minus 6. Is this a polynomial?
Should we have the square root and be going on? I forgot.
Well, it's the answer to that question is it depends.
I don't think it's a polynomial.
This is a polynomial.
Is it?
It is. Yeah, so if we look at the coefficients, those are both real numbers, right? Root 3 is a real number. Negative 6 is a real number, so that's okay. The exponents are non-negatives, 1 and 0. The only operations going on in between the coefficients and the variables is multiplication, and then we have addition or subtraction between the terms. So it's good. That's no problem. Yes, this is a polynomial. So in this case, what's the leading coefficient?
3. No. Yeah, 3.
Root 3. And the degree then is?
0. Or 1.
1. Yeah. Because really, that's an x to the first there, right? Now, just as an aside, if this was 3 square root x minus 6, that would not be a polynomial. So if the radical's over the x, that's no bueno. But if the radical is just over the 3, like it was in that, in g of x there, we're good, right? The radical can be over the coefficients, that's fine, but it can't be over the variable. Cool? So Joe, you asked if it can have a radical, and that's kind of why I said it depends.
So that's the situation.
Yeah, the radical over the number, over a coefficient, no problem. Radical over the variable, problem.
Okay.
Does everybody feel good? Okay. Let's look at h of x. This is just like I'll put aside here, because this is just like a hypothetical. H of x, what's our conclusion here?
Yes. Should it be? Or no? I think yeah.
What do you guys think? Joe says yes. I think Ellie shook her head no. Anybody else have an opinion? Becker's saying no. Eric says no. No is the answer.
It's not.
What's the problem? Yeah, we have a x is underneath the radical. So the thing we have to be cautious about here is the radical is over variables.
Oh.
So that's our why we're going to say no. Now, some of you might have said, oh, well, why can't I just like square root this all and just write it that way? Then it's a polynomial, right? What's wrong with that? Hi, Megan. Oh, Ariana, you got some mail.
Thanks.
You're welcome. I know you get mail at school, but you managed to do it, so good on you.
Hey.
But what's wrong with what I just did there? At first glance, this looks really feasible, right? And if I do that, 3x squared plus 4x is definitely a polynomial. But Mr. Kulik's telling you can't do what you just did here. What's the issue? No. The issue is that this addition symbol in between, you can't distribute a square root symbol across addition or subtraction. Basically, what we're saying is that the square root of a plus b is not the square root of a plus the square root of b. That's not true. So that's why I can't do what I just did there. So that's, again, just like an aside. Just reviewing some algebra concepts here along the way, because these are things I see frequently students make mistakes with. You know what I mean? Very tempting to want to distribute that radical, right? like Mr. Kulik did, and it's like, I don't know, what's wrong with that? We distribute things all the time. No, we really don't. The only operations, the only functions that distribute is multiplication, division. That's all you have. You can't distribute like sines and cosines. You can't distribute radicals. You can't distribute logarithms or exponentials or anything else that we've talked about. Addition, subtract, or multiplication, division. That's it. Anyways. Again, we took some side tangents there, just talk about some other stuff, but that's okay, right? Again, I think going back and revisiting some of these algebra concepts is helpful. K of x equals 5x squared plus 6x plus 2x to the negative 1 plus 5. Is that a polynomial? No, why not? Yeah. That's our problem. Keep in mind that you could have also that this is also the same thing, right? The negative exponent just makes a reciprocal. And this is also not a polynomial. What's the issue with this? If I write it this way, I'm dividing by a variable. You can only multiply constants and variables. You can't divide. Now, if it was x over 2, would that be okay?
No.
That is okay. Let's think about why that's okay. So if you think about that, x over 2 is the same thing as 1/2 x to the first, right? You guys see that? And 1/2 is a real number, x to the first, positive exponent. That one is okay. So the takeaway there is x's in the denominator, variables in the denominator, bad. Numbers in the denominator, that's fine. No big deal. You guys see that? So again, just kind of, talking about some other examples, some hypotheticals there. Okay. So we have some common names that we give polynomials. And there's two major ways that we'll name polynomials. One is by their degree. So if the degree is 0, we call this a constant polynomial. An example of that could just be like f of x equals 7 or something, where there's no x's at all. For degree equals 1, we call this a linear polynomial. So an example of that could be anything in that y equals mx plus b kind of form, like y equals 2x plus 5. The degree is 2. That's a quadratic polynomial. So maybe you have something like 3x squared minus 2x plus 6 or something. Right? The biggest exponent there is 2. The degree is 3. We call that a cubic. And the last one we'll worry about is degree 4. That's called quartic. And I think probably at this point you get the idea of where we're going here. So constant, linear, quadratic, cubic, quartic. The other way we can name a polynomial is by the number of terms. So if we have one term, we call this a monomial. So like 4x squared is a monomial. 2 terms, we call it a binomial. So maybe like x to the 7th minus 2 is a binomial, has 1, 2 terms. 3 terms, we call that a trinomial. So like 7x to the 4th plus 2x squared plus x is an example of a trinomial, has 1, 2, 3 terms. God bless you.
Trinomial.
Okay, so we have 3 terms. And the degree is?
Leading degree, or whatever it's called, is 4, but
Yep.
it's called quad. What's it called? What's called quartic?
Quartic, like quarter.
Okay, quartic.
So we call this a quartic trinomial. Okay with that? Fairly easy, right? You just got to kind of get used to the naming. Let's do one more. Okay, what do we see here?
2 terms.
Okay. And the degree? So we call this then a cubic binomial. Everybody feel okay there? We'll do that. If you're going back and looking at it, that might be helpful to figure out how we're using that information to come up with the names. All right. I'm going to stop here. So you guys should be able to do 1 through 4 from the problem set. But we're stopping here because I want to give some time in class, because many of us have like multiple missing or incomplete assignments. So I want to give a little bit of time here in class and just say like, hey, catch the heck up.